Among his many titles, he was the founding director of the Gatsby unit in University College London. He is university professor at the University of Toronto, and he was also a recently appointed distinguished researcher at Google. Of course, Jeff is one of the founders and the main name in the field of artificial neural networks, as well as in the field of machine learning. His coming at MIT is also a bit of an event. For those of you who were at the talk at CSAIL yesterday, there was 500 plus people, and basically people couldn't get in. Today we're starting at 4 because I'm sure it's going to be a similar effect. There's also a panel discussion that Tommy is organizing at 6 with Jeff in this same room about path to intelligence. So I won't say much more because we all came to hear him. Just to say that the ransom of success might be what you see on his webpage, which says information for prospective student. I will not be taking any new graduate student, visiting student, summer student, or visitors, so please do not apply to work with me. Jeff?
Thank you so much. If, however, you'd like a job at Google, that's something else. So there's a lot of things wrong with the neural nets we're using. They've been quite successful at speech recognition and object recognition, particularly recently. But there's a lot of things that are very unlike the brain and that I believe are making them work not as well as they could. So one thing wrong is any complex engineered system should have various levels of structure. Neural nets have very few levels of structure. There's neurons, there's layers of neurons, which aren't at all like layers in cortex, and there's whole neural nets, and that's it for most of these neural nets. One thing that's missing in these neural nets is there's no explicit notion of an entity. So for those innatists in the audience, I am willing to admit that it might be worth building into a neural net something to do with the idea that there are entities. And I want to build that into the architecture. That's what this talk's going to be about. So what I want to do is take the neurons in what we call a layer and group them into subsets and have activities of neurons in those subsets represent different properties of the same entity. I want the neural net to decide what the entities are and how they interact with each other, but I want the sort of built-in property that there's going to be entities. That's all I'm going to concede to the innatists. I also want to push the idea that a mini-column is the place where you represent an entity. One entity per mini-column. And I'm going to call this thing in the artificial nets a capsule. And the idea is a capsule is going to have two kinds of instantiation parameters. It's going to have one that says whether its entity is present. I'll talk about images mainly, so in the current input image. And then it's going to have other things that describe properties of this entity. If the entity is not present, you can say all you like about the properties, it doesn't matter. But if the entity is present, then you want to know its properties. And the properties are going to be things like its orientation, its size, its velocity, its color, all sorts of things like that, its deformation. And what a capsule outputs that goes to higher level capsules, because I want this in a hierarchy, is the probability that the entity is present and the generalized pose of the entity, which in vision is going to be an object or part of an object. And that includes all sorts of parameters. And what capsules do that does not go on in normal neural nets, this is the sort of basic computation they're meant to do, is they take predictions from lower level capsules about what their generalized pose should be, so about a multidimensional vector, and they look for predictions that agree tightly. And they don't care if there's lots of predictions that are outliers. What they're concerned with is there are a small subset of predictions that agree well. If you did computer vision many, many years ago before it got silly, this is things like Ransack and Huff transforms. So a capsule, it has a high dimensional pose space, maybe 20 dimensions or 50 dimensions. So this is a picture of that space. So this is a 20-dimensional space, let's say. And there's predictions coming from capsules below. And these are the predictions. These are the vectors that are predicted for the pose of this capsule. And what we want is something that will find this cluster. And what it'll output is, it'll output a probability that says, hey, I really am present, because look, that didn't happen by chance. I'm really there. I've got lots of evidence that I exist. And I'm going to output the center of gravity of that, and I'm going to ignore all these. And neural networks at present are not good at doing that. They may somehow be able to fake it, but they're not built to do that kind of thing. Now, the point about high-dimensional coincidences is they don't happen by chance. Even if I have a 6-dimensional thing, and I have two 6-dimensional things that agree on every dimension to within 10% relative to the normal variation, then there's a chance of 1 in a million of that. So if you see a few things that agree sharply, it's not this coincidence can't just be a coincidence, if you see what I mean. There's something really must have caused it. A model of this is if you think about filtering intelligence information, if you see all sorts of conversations that say New York or say September, that doesn't mean much. But if you see a whole bunch of conversations, maybe just 4 of them, that say New York, September the 11th, and you see 4 of those, you should get extremely suspicious, because now it's a high-dimensional coincidence. And even if there's lots of other things that say Chicago and blah, 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 the fact that it's high-dimensional and it's a coincidence should make you think there's something real going on. OK. And I'm going to argue that I'm going to take a Marian perspective and say, in order to understand the brain, we need to figure out what it's computing. And I'm going to give you a reason why the brain needs to do this computation. And then I'm going to suggest this is what mini-columns are doing. It's wild speculation, but at least it's Marian wild speculation, because it's based on, it comes from the computation that needs to be done. OK, so here's how neural nets currently do object recognition, and do it very well, compared with methods that are even worse. This is largely due to Yann LeCun, who since 1987 has been getting backprop to do this and has developed the technology a lot. He calls them convnets. And they use multiple layers of learned feature detectors. So that's good. And the feature detectors are local. The locality gets bigger as they get bigger domains as they go up. They're replicated across space, because you believe that if a feature is worth having here, it's worth having there. That's good. As you go up, the spatial domains of these feature detectors get bigger. That's good. And the feature extraction layers are interleaved with max pooling layers, or average pooling layers, or some kind of pooling layer. And what the pooling layers do is they say, I'm a pooling neuron. I'm going to look at the neurons in a layer, look at nearby ones, and I'm going to attend to typically I'm going to attend to the most active one. It may be probabilistic, but let's say I just attend to the most active one. So I'm going to report the activity level of the most active one and forget where it was. That's going to give you a small amount of translational invariance, and it's going to give you less active neurons, so you're going to be able to have more feature types at the next layer. This is what I don't believe in. This is an integral part of the things that work really well. The fact that it works so well is extremely unfortunate, because it's going to make it harder to get rid of. But that's just the way it is. So as I was saying, the pooling gives you some translational invariance, because it throws away where the most active feature is. Actually, it doesn't have to lose positional information if you have lots of pools that overlap. But if you do that, you get less advantage from reducing the number of units. I'll leave it at that for that. Now, if you take these convolutional nets, I kind of showed yesterday that with one of these convolutional nets, you can take the activities in the last hidden layer. If it's been trained to recognize lots of different categories of object, you can now train it. So this is a repeat of what I said yesterday, just briefly. You can train it with a recurrent neural net to actually give you a caption. And I'm going to skip a bit here. Well, I'll just show you what it does. So you show it this, and you ask it, what do you see? And the recurrent neural, in effect, and the recurrent neural net says 2 pizzas sitting on top of a stovetop oven. If you run it again, it's stochastic. It'll say a pizza on top of a pan on top of an oven. Whether or not it really understands these relations, or whether that's just in the language model, we don't yet know, because it's learned to model language as well. But that's just to show you convolutional nets can do impressive things. There's another caption. And now here's why I don't believe in the pooling. I believe in the convolution, I just don't believe in the pooling. It's a really bad fit to the psychology of shape perception. There's things about the psychology of shape perception that argue very strongly that we're not using convolutional neural nets. It's solving the wrong problem. We do not want the neural activities to be invariant to viewpoint, at least not till the very top. What we want is that the knowledge is invariant to viewpoint. The same knowledge can get applied to something with a new viewpoint. That doesn't mean the activities have to be invariant to viewpoint. I'll go over each of these in more detail later. The worst property of convolutional nets is they fail to use an underlying linear manifold, which is going to make it very easy to deal with the effects of viewpoint. It's the linear manifold that's used in computer graphics. Here's a piece of natural reasoning. There's two things that have no problem with viewpoint. One is us and other brains, and the other is computer graphics. And therefore, they work the same way. Okay. And the last thing is, pooling is a very bad way, or a very primitive way, to try and do routing. So in vision, what happens is as you change the viewpoint, the same thing shows up on different pixels. That's not usual in machine learning. If you change illumination, for example, that doesn't happen. But when you change viewpoint, you've moved information from one set of pixels to another set of pixels. So that's what I call dimension hopping. And for machine learning, you better unpick that, otherwise you're not going to be able to make any sense of things. Imagine two hospitals, and one codes patients by age, weight, and financial status, because it's America, and the second codes patients by weight, financial status, and age. If you just took those records and applied machine learning without sorting that out, you wouldn't expect it to work very well. But in vision, that's exactly what viewpoint's doing, and we'd better sort it out. And that's a routing problem. We need to take the information of the pixels and route it correctly to the neurons that know how to deal with that kind of information. And people haven't really, most neural net people haven't really faced up to the problem that we're having to solve a routing problem. People doing part space models have faced up to that, but not the convolutional net people. So I'm going to go over these four arguments now. The talk is mainly going to be about trying to convince you that convolutional nets are no good, even though they work very well. Or rather, the max pooling aspect of convolutional nets is no good. And I'm going to start by saying it's a bad fit to the psychology of shape perception. So when people do shape perception, they do it by imposing rectangular coordinate frames on things. And if you take the same object and you impose a different rectangular coordinate frame, you don't even realize it's the same object. That's how much effect it has. I can show you an object and show you exactly the same object again with exactly the same retinal image. And if you impose a different coordinate frame, you won't realize you've even seen it before. It's a huge effect, and convolutional nets just can't explain that. They can't explain how the same pixels can be processed completely differently depending on the coordinate frame, because they've got no notion of imposing a coordinate frame. Now, this isn't necessarily quite true. It may be that neural nets are so powerful that with these multiple layers, they kind of fake imposing coordinate frames, and we don't know whether that's true or not. But let's suppose it isn't. So I'm going to try and give you a demonstration that illustrates the power of coordinate frames. Here's something you wouldn't believe. I take a simple object like a tetrahedron. A tetrahedron is a pyramid with a triangular base. And I slice it with a plane. That's a flat thing. I slice it with a plane, so I get two pieces. And then I take an intelligent person, and I give them the two pieces, and I say, OK, make the tetrahedron. And I make sure they know what a tetrahedron is, and they can't do it. Now, that clearly means that, now, you don't believe that, presumably. It's just two pieces. Surely you can put them together to make a tetrahedron. Well, I've been doing an experiment today on MIT professors. I got one sample 30 years ago, and that was a professor called Carl Hewitt, who was very smart. I gave him the two pieces, and he looked at them for a long time. He didn't manipulate them. He looked at them for a long time. After 10 minutes, he wrote down a proof it was impossible. So his time to solve the puzzle is infinite. Okay? Today, I've been doing experiments on MIT professors, and the number of minutes they take to solve the problem is about the number of years they've been at MIT. Roughly speaking. It's definitely the length of time is very positively correlated with how long they've been at MIT. So now I'm going to show you this puzzle, because it's extraordinary it can be so hard, because it's completely trivial, and there's a very obvious way to solve it that people don't figure out. They figure it out after a few minutes, but OK. Here's the two pieces. Right, I can do my sort of conjuring trick now. These two pieces, see, they're the same. And here's what people do. They say, OK, tetrahedron. Yeah, like, well, that's not a tetrahedron. Wait a minute. That's not a tetrahedron. And then they try sticking the ends together. And then they do this. And they really do this, and people have witnessed them doing this. They do that and say, well, that's not a tetrahedron. Well, what about that? That's not a tetrahedron. And after a few minutes, if they're young, they go, oh, right, that's a tetrahedron. So now, why is this puzzle almost impossible? Why is it so hard? Because it's a two-piece jigsaw puzzle. And they're MIT professors. And, oh, incidentally, I tried this on a Google vice president, just to reassure the MIT professors. I gave the two pieces to the Google vice president, and I said, it's a really hard task. Can you make a tetrahedron? And he said, yes. Honestly. So they didn't pay me to say that, it's true. So how could this be so hard? Because look, you know it's all made of triangles, the faces. And look, here's a couple of squares. So you've got to put the squares together, because you've got to get rid of those squares somehow. So you have to put the squares together, and everybody does that. And when that doesn't work, they do that. And that doesn't work either. It doesn't work. And why don't they do that? Well, the answer is, when I show you this piece, there's a natural coordinate frame. And you can see the natural rectangular coordinate frame for this piece. It's got a long axis, and it's got an axis across and an axis up and down. And that coordinate frame does not line up at all with the natural coordinate frame you use for tetrahedron, unless you're over 15 and went to an American public school. If you're over 50 and went to an American public school, you would have got milk in tetrahedral cartons that were stacked, and they were stacked like, whoops, they were stacked like that. And you have a model that says it's a line there, a line here, join up all those lines, and a tetrahedron looks like that. And if you also have that model, which I'll call a quadrahedron because it's so different, then it's obvious that if you slice it here, you get a long, thin rectangle that way. If you slice it there, you get a long, thin rectangle that way. And some mathematician said if you slice it halfway, it better be in between. And so you better get a square somewhere. If you have that model, I'll call it the quadrahedron model, this puzzle is completely obvious. And a crystallographer will do that instantly. But a normal person just can't do this puzzle. And it's because the frame of reference they use for a tetrahedron doesn't line up with the frame of reference you naturally impose on one of these pieces. There's other subsidiary things, like the pieces have a different relationship to the whole. And you don't expect that. Because they're symmetrical, you expect to have a symmetric relationship to the whole. Anyway, that's it. That's the end of my evidence that convolutional nets are not psychologically correct. Yeah, that's sufficient to convince me. Show you the puzzle. Irving Rock pointed out all this stuff a long time ago. If you show people a map like this and ask them what country it is, most people say, well, it's a little bit like Australia, but it's not Australia. But if you tell people, what country do you think Sarah Palin might think this is? People who are politically savvy, they say, this is Africa. Sarah Palin actually thought it was a country. And if you see the top here, then it's immediately obvious it's Africa. But if you impose the top wrong, you don't recognize it. And the very familiar example is a tilted square. If you see it as a tilted square and you see it as a diamond, it's two different internal objects. If you see it as a diamond, you're totally unaware of whether this is a right angle. I can make that be 85 degrees or 95 degrees or 90 degrees. None of them looks better than the other. If you see it as a tilted square, you're accurate to within about 1 degree on whether that's a right angle. So lots of evidence for rectangular frames, and convolutional nets don't use them. one more bit of evidence. Okay, so that tells me that people's visual systems are recognizing things by imposing rectangular coordinate frames and probably a hierarchy of them, just like computer graphics does. Computer graphics has to say what the relation is between a part and a whole, and so it has to impose a frame on the whole, impose a frame on the part, and then tell you the matrix that will map points in the whole relative to the frame of the whole to points relative to the frame of the part. So it's all linear, that's the linear manifold, but you can only express it by imposing this coordinate frame. Luckily, there's a chance in the discussion later when Tommy can point out how what I say is all bullshit. I can read his mind. Now let me give you some more evidence, and this is evidence not only do we impose coordinate frames, but we represent the imposed coordinate frames by a bunch of separate neural activities, not by having one neuron that says, I'm imposing this frame. I want to show you it's in a bunch of different neural activities. So suppose I show you this. What you know within about 250 milliseconds or less is that it's a capital letter R and the top is here. What you don't know is whether it's a correct R or a mirror image R. And to figure out that, what you do is you go chunk, 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 chunk until it's upright. And then when it's upright, you say, it faces the wrong way. So it's a mirror image R. And why is that? A more impressive demonstration of that is if you go with a woman to a fancy shoe shop and you show her a shoe, she can tell you within about 250 milliseconds how much it costs, who made it, which other stores it's available in. This is a bit sexist, but there you go. She can't tell you whether it's a right-hand shoe or a left-hand shoe. Now that's extraordinary. I mean, she knows all these properties of this shoe, but she doesn't know whether it's right-hand or left-hand. She has to do this kind of chunk, chunk, chunk to get it in canonical orientation. So how could that be? So my argument is that you know the relationship between this and the viewer. Okay, so you have the pose of this in viewer-centered coordinates, and you need to know whether the matrix that relates the intrinsic frame of this to the viewer frame is a left-hand one or a right-hand one. And if you have the matrix represented by a bunch of separate numbers, like they do in computer graphics, to know whether it's a left-hand one or a right-hand one, you need to know the sign of the determinant of the matrix. In other words, you need to solve a high-order parity problem. Reversing any one changes the answer. If you reverse the value of any one number, the answer is changed. So neural nets aren't good at high-order parity problems, so that's why we can't do handedness. And the fact that we can't do handedness, I take as strong evidence that our representation of the imposed coordinate frame, of the relationship between that and the viewer, is spread over many numbers, just like it is in computer graphics. Okay. And so the way we solve it is we do a continuous transformation that preserves handedness until we've got it down to just checking one direction and seeing which way it goes, and then we solve it, and that's how we do it. And so all those mental rotation things, they're not to recognize objects, they're to deal with this problem that you don't know the handedness. Okay, so the conclusion for argument one is people use rectangular coordinate frames embedded in objects and embedded in parts of objects, and they represent those coordinate frames, that is, they represent the pose of the object, the relation between its embedded coordinate frame and the viewer. They represent that spread over a bunch of numbers, not just in one neuron. Argument two, equivariance. What convolutional nets are trying to do is make the representation not change with viewpoint. And of course, that's what you want the label to do. But when you look at a face, for example, it's not that you say face and I don't know where it is or what its orientation is or what its size is. You look at a face and you know exactly what its orientation is and exactly where it is. So you haven't lost that information like convolutional nets try and do. You've got it all there very precisely. Now, many neuroscientists think if you have big receptive fields, that means you've got low accuracy. That's exactly the opposite of the truth. If you want to have very high accuracy for where something is, and you have a limited number of neurons, you should make them have very big receptive fields that overlap a whole lot. You'll get much higher accuracy that way because you'll divide space into many tiny regions, and the number of regions you make is proportional to the surface area of these receptive fields, and to get a lot of surface area, you make the fields bigger. So the signature of wanting really high accuracy for these instantiation parameters is that you should have big fields. Of course, you lose resolution, so you can only afford to do that for things where there aren't many of them. You can't do it for edges, because there's too many of them around, and you don't want to lose the resolution. But as you go up to high-level things like faces, in some reasonable area, there's only a few faces, so you can have big fields. Okay, so what we want is we want a representation where, as you change viewpoint, the neural activities change, and they change just like the viewpoint does. So convolutional nets without max pooling are like that. They say they got viewpoint invariance, but not at all. Here's a 2, and here's the neurons that get active. You translate the 2, and the neurons that get active translate. It's the same pattern, but it's different neurons. This is equivariance, right? You change this, and this changes, and it changes the same way. Okay. Now, I want to distinguish two types of equivariance using pseudo-neuroscience terminology. In this, if we translate it by a whole number of pixels, then these will move across. And this is what I call place equivariance. As you change the pixels this is on, the neurons that represent it change. Call that place equivariance. There's a different kind of equivariance, which is rate-coded equivariance, which says as I move the object around, the same neurons are encoding it, but the activities of the neurons is changing. Okay, so it's a rate code rather than a place code. And what's happening in the visual system, is my belief, is low level, we have very small domains, so tiny changes change the rates, and then if you change by more than a tiny amount, you change to another neuron or another bunch of neurons, another capsule, and so that's now place coding. It's sort of like cell phones with little cell domains. You move around a little bit and it stays in the same domain, and then you jump to another domain, and you move around a little bit in there. As you go up, these domains get bigger, so when you're at a high level, you can move a long way without changing which neurons are coding it, but the activities of the neurons changes to tell you where it is. Okay. Now, argument 3. I think this is the most powerful argument. If you ask how current neural networks deal with invariance, what they do is they just train on a lot of different viewpoints. And that's quite sensible. It just requires a lot of training data, and going through a lot of training data takes a lot of time. They don't have a built-in bias to generalize in just the right way across viewpoint. So I guess this is another piece of innatism. I'm getting soft in my old age and allowing these tiny little... You allow those innatists to get even a foothold on your model, and pretty soon they'll be infecting it. Okay, so a much better approach would be to say there's a linear manifold, which is what computer graphics uses. If we get from pixels to the coordinate representation of pieces of objects, or objects, that is, it's this kind of thing, and here's its pose in a bunch of numbers, then everything's linear in that. And now you can do massive extrapolation. You can train on little faces like this here, and then I can show you a huge upside-down face, and you'll correctly recognize it. Because on the linear manifold, you can extrapolate. That's what neural nets can't do, and if they could do that, we could train them on a whole lot less data. Okay. So the idea is, a long time ago, and for many years, people have been saying, you can think of vision as inverse graphics. But they didn't mean it literally. And I want to do it literally. I want, inside my system that does computer vision, I want it to be doing graphics backwards. When graphics takes a whole, and takes the pose of the whole and multiplies it by a matrix to get the pose of the part, I want my computer vision system to be taking a part and taking the pose of the part and multiplying it by the inverse matrix to get the pose of the whole. That's what I call inverse graphics. So when I say it's literally doing inverse graphics, I mean literally, literally. Okay. And if you do that, then you can represent the relationship between a whole and a part as just a matrix of weights, and that matrix of weights is completely viewpoint invariant. So however much I change the pose, it's the same matrix of weights that takes the pose of the whole and gives me the pose of the part, or it goes the other way, the pose of the part and gives me the pose of the whole. So I've got complete independence of viewpoint in the weights. That's where we want the invariance. We don't want it in the neural activities, we want it in the weights. And we can get perfect invariance in the weights this way. Now, this is messed up by the fact that if you have multiple instances of the same entity, you've got to have small domains, because you have to code multiple ones. And each of these capsules can only deal with one thing at a time. Because it's using simultaneity to do the binding, it's saying within my capsule, I've got a bunch of neurons. The activities of those neurons represent different properties of the same thing, and there better only be one thing. And so when things are this far apart, you need fields this size. When things are this far apart, you can use fields this size. You can make the fields overlap a bit and fudge it a bit. But if you violate that, your perception is going to go all wrong, and that's called crowding. If you put things too close together, you're very bad at seeing them. You're better at seeing smaller things further apart. But I'm not going to push that. So, given this view of the world, here's how you ought to do shape recognition. And this is computer vision from the 1980s. You identify some familiar part, like a nose. And you have a logistic unit that says what's the probability that it's there. So this varies between 1 and 0. So it's true this is invariant, but just this little bit. This guy in here has the pose parameters of the nose. So if we just think geometrically, this will be, say, 6 numbers in here that tell you the pose of the nose relative to the viewer. You then have a matrix that operates on this pose and gives you a prediction, this thing here, for the pose of the face. Here you've got an identified mouth. You have the pose parameters. You operate on them with this completely viewpoint invariant matrix, and you get another prediction for the pose of the face. If those predictions are roughly the same, that's very good evidence that there's a face. Those predictions will only be roughly the same if the nose and the mouth are related in the right way to make a face. So really, by checking this identity, you're checking that these are related correctly to make a face. And if they are, you say, hey, there's a face here, and you send out the average of what they predict, the average of this and this, and you make this be 1, and you carry on. So this is a way of doing coincidence filtering to recognize larger parts from smaller parts. And this is very robust. There can be other capsules that are making different predictions for the face, and you will just ignore those. If you have a way of finding the little cluster that agrees among a lot of noise. And old-fashioned visual people will say, why isn't this just a Hopf transform? That is a Hopf transform. That's what Hopf transforms are all about. And it is just a Hopf transform. But it's a modern Hopf transform in the following sense. In the old days when they did Hopf transforms, they would have fairly low-dimensional features trying to predict the high-dimensional poses. And if the dimensionality of the feature is lower than the dimensionality of the object, you have to predict a subspace. And so you have to have bins, and you have to put lots of votes in lots of bins. If you just want to make one vote, so you don't need all these bins, then you better have it that the features have as many dimensions as the high-dimensional things. And to get features like that you can reliably extract from pixels, you need machine learning. You need good machine learning. And the reason they couldn't make Hopf transforms work before was because they couldn't get the low-level features to have enough dimensions and be reliable so that they could make point predictions. Okay, that's my claim about why this is different from old-fashioned Hopf transforms. But it is a Hopf transform. And the last argument I want to make is to do with this routing. So the idea is, what viewpoint does is it changes where things show up in the image. And so a nose is here now on these pixels. And let's suppose it was a face. And let's suppose you just have one great big face capsule at the top. So you need to route these pixels to the face capsule. And in a different image, you need to route these pixels to the face capsule. And I want to show you there's a nice way to do routing. So the first order of doing routing is you make an eye movement. You put what you're interested in the middle of your retina. And that's a very powerful routing algorithm. But even if I I do a tachistic scope, so I force you to fixate in one point, you can still do routing. And here's how you might do it. Well, if you take convnets, I already mentioned this. The way they do routing, they have a pooling unit, and it just attends to the most active guy, and the same all these levels up. So that'll route things, but just based on how loud they are. I want a routing principle where you route information to the capsule that knows how to deal with it. So the idea is that you assume that, we're going to assume the world's opaque, we're going to assume that it can be modeled by a parsed tree, so we're going to assume each part that we discover has one parent, that's the single parent constraint, or possibly no parents, but it doesn't have multiple parents. So we want to find what it's a part of, and there's just going to be one of those. And so when you discover a part, suppose I discover a circle. A circle, I suppose I have a limited world that contains only cars and faces. A circle might be a left eye of a face, it might be a right eye of a face, it might be the front wheel of a car or the back wheel of a car. And I don't know from the circle which it is. So what I'm going to do is take the pose, and I send it to all those places, but I'm going to send a kind of weight with that, which says my bet is a quarter that it's this, and a quarter that is that, and a quarter that is that, and a quarter that is that. So you send it to these high-level capsules, lots of weak bets, and then what the high-level capsule needs to do is look at all these incoming weak bets and find a bunch that agree. And when it finds a bunch that agree, then, so the low-level capsule is sending its pose to several higher-level capsules, and initially it weights by the prior. So there's going to be a prior which, a circle might be part of a face, it might be part of a car, it's probably not part of a fridge, so you don't send it to the fridge, or you send it with very low weight to the fridge, and with higher weights to a face and a car. Then in these capsules, you find the clusters. This is a magic computation. I'm not telling you how you do this computation, but let's suppose we can do this magic computation. Like I say, this is a Marian approach of what computation do you need to do, and that's what we're going to suppose a capsule does. And we reason about this computation from the nature of the task, and then it's somebody else's problem for how it does it. Well, it's my problem, and I can't make it work very well, but here we go. I'll show you how I do it currently later. So you sent it here, and it was this blue prediction, and it agreed with the cluster. You sent it here, and it was this prediction, and it didn't agree with the cluster. So now what you want to do is you want to send top-down feedback, or you want to have lateral interactions that say, let's suppose it was top-down feedback. The top-down feedback from this capsule says, send me more. I can account for this stuff. Please send me your output. And this guy says, I can't account for this stuff. Please don't send me your output. And a few iterations of that, and you'll be sending all of the output of this guy to here and sending none of it to there. And now you will have a parse tree. You will have established that this belongs to that. There's obviously competition, but yeah, I'm trying to get the basic ideas over here. So that's my proposal, either by lateral interaction between these two guys, saying that the weights on them must add up to 1, and this guy fits in nicely, so he'd like more weight, and this guy doesn't fit in nicely, so he'd like less weight, so give this guy more weight and this guy less weight. Or you could do that by top-down. But notice the top-down isn't going to be like loopy belief propagation. It's not going to say, I'm going to use this to revise my opinion about what's here. It's just going to use this for routing. It's going to say, OK, this capsule can account for me very nicely. I want the information from here routed to this capsule. So it's a routing by agreement algorithm. And it's using consistency to do the routing, as opposed to just saying, I'm going to ignore everybody but the loudest guy that I can see, which is what max pooling's doing. So now I'm going to show you two computer programs. Unfortunately, one of them was written by me, so it's not a very good program. It runs very slowly. But the idea is that if we could make this basic module that can check high-dimensional agreement and throw out outliers, then we could have a deep system. We've got a front-end problem, which is how do you get to the first things that have poses? That's what I call de-rendering the image. It's getting from pixel intensities, which are to do with light, to the poses, which are to do with geometry. And then the higher levels are all going to work the same way. They're going to put pieces together into larger and larger pieces. I'm going to have a not very deep system to begin with. But what we want to do is be able to use the power of stochastic gradient descent and lots of data to learn a parts-based hierarchy with no hand engineering other than what I said already, other than putting in this idea that there's going to be coincidence filtering and rerouting based on agreement. So here's my proof of concept. I'm going to take MNIST digits, and I'm going to have little patches. It's going to be convolutional in the following sense, that in the first stage, I'm going to take a patch. It's going to have some weights, connecting it to some hidden units. And that's the black patch. There's going to be a blue patch. It's going to have exactly the same weights, connecting it to 300 blue units. Okay, so the way I process a patch is completely the same wherever the patch is. That's convolutional. These are going to be nonlinear units, and what I'm going to ask these units to do is to give me the poses of, I actually use 7, but I've shown 3 here, the poses of 3 different types of capsule. So capsules that detect different kinds of entity. This might be vertical edges, horizontal edges, corners, or something like that. I'm not going to specify what these entities should be. I'm going to learn it all by gradient descent from the right answers. But the way the first stage of the system is going to work is it's going to convert some pixel intensities into some vectors of pose parameters, pose instantiation pose parameters. And these are going to be different pose parameters. They're going to be pose parameters of different kinds of things. In addition, it's going to say whether it thinks this thing is there or not. So that's going to be a logistic unit. And everything's going to be learned, but it's all going to be shared across the image by all these patches. And these are going to be linear units. Now, those things are going to be what I call the primary capsules. They're the first level of capsules. They're the first level at which you have explicit pose coordinates. And I'm going to have a very flat system to begin with. It's just got 2 levels. It goes from that first level to a second level. I've made deeper systems, but this is the easiest one to understand. In the second level, it has a bunch of capsules. There should be the same number of guys here as there are there. I was just lazy with the PowerPoint, okay? Sorry about that. I should have put more things in here. So you take a type A primary capsule that's looking at the black patch. You've extracted some numbers from it. You've learned to extract these numbers. We'll say how in a minute. And you apply a coordinate transform to that vector of pose parameters to make a prediction for the pose of the 0, if there's a 0 there. Also, from whether or not this is active, you make a prediction for whether the 0 is present. That's what I call a Picasso weight. So a Picasso weight says, let's look at the type of the capsule and predict whether this thing is present solely based on the type and ignoring all geometric constraints. So if you see an eye, there might be a face. And even if the eye's in completely the wrong place, if I put enough eyes and noses around, you'll see a face. Or you'll think there's sort of a face there, even if the geometry is all wrong, just because eyes go into faces. So this is the reason it says, because it's an eye, there might be a face. This is doing the real work. It's saying, I take the pose of this feature I've identified, this high-dimensional feature, and I predict the pose of the 0. And you're going to do the same from all of these different primary capsules. And you also have a weight on this prediction. So this is a weighted bet. And now, for the same patch, for the same black patch in the original image, I'll have a type B capsule that is detecting a different kind of feature, and it's making predictions. It's predicting the pose of the 0 and the pose of the 1. And as well as having the predictions that come from the black patch for the different types of feature, I have predictions that come from all the other patches from the different types of feature. so a type A feature and a type B feature. From the red patch, you're making predictions. So I get a whole lot of predictions here. And in particular, this weight matrix that relates this pose of a type A feature in the black patch to this prediction is going to be the same as the coordinate transform for the red patch to make a prediction. And that's not quite right, so we have to fix that up, because the red patch is in a different place. And so it ought to predict a different pose. And so we have to fix up the translational bit. And we're going to do that by saying, when I make my prediction from this primary capsule about the pose of this digit, I'm going to take the first two coordinates, I'm going to say their position, and I'm going to add on the location of this patch in the image to the first two coordinates. I'm just going to add it to whatever this computes. And so that's the offset you get in the position due to the offset of the patch. Everything else about the patch is the same, but as you offset the patch, it should offset where you say the thing is. And that's implemented by this. It also means these first two coordinates are going to be interpretable. So that's the whole system. And now what we want to do is say, if you get a whole bunch of agreements here, it's a 0. If you get a whole bunch of agreements here, it's a 1. And so we want to backpropagate. We know what the class is. Let's suppose it's a 2. We want lots of agreement here and not much agreement there. So we need some measure of agreement, and we need to be able to backpropagate it. And we need to say, if you're not getting much agreement here, please get more. And if you're getting too much agreement here, please get less. And then we can learn all of these weights. We can learn the weights that turn pixels into the poses of primary capsules. We can learn these coordinate transforms. That's fixed for now, so we don't learn that. And we learn various biases and things. So.
Geoffrey, question. In the previous first layer of capsules, you had this 300 sigmoidal units.
Yes.
Is that also in the second layer of capsules as well?
No, because if you want to get from pixel intensities to the poses of features, that's highly nonlinear. This is getting the coordinates of a feature from pixel intensities. But if you want to get from the pose of a feature to the pose of a larger thing containing it, that's completely linear. So you really, really don't want any nonlinearity in there. It's a very good question. So in this little system I implemented, each of the high-level capsules, there's 7 feature types. There's 181 patches in the image, and it gets that many predictions. It gets a whole lot, many of which are very weak. So it's organized so that blank patches make very weak predictions. And coming with each prediction, there's a bet about, so for any one primary capsule, it makes predictions, and the sum of the bets for this prediction add up to 1. And this is treated as a fraction of an observation for what comes next. The high-level capsule then is looking for agreement. And so we need some way, with all these bets, with these over 1,000 bets coming in, we need some way to find a subset that agree nicely. And so what we're going to do is we're going to try and compute for this high-level capsule whether it's got good agreement. And the way we're going to do it is in this pose space for the high-level capsule, we're going to fit a mixture of a Gaussian and a uniform to the predictions. Let's suppose it's a 6D space. And we're going to ask, how good a model is that of my predictions compared with how good a model do I get by just fitting a uniform? And if when I fit a mixture of a Gaussian and a uniform, I get a much better prediction, a much better log prob for these predictions. So we treat it as a kind of unsupervised learning problem. You've got all these predictions, I want to build a model of them. And I have 2 alternative models. One is just uniform. The other is uniform and there's a Gaussian somewhere. And I'm going to allow the mean of that Gaussian to float around. So as this neural network is running, the mean of its Gaussian is floating around, and the variance of its Gaussian is floating around, and the mixing proportion of the Gaussian is floating around. What isn't floating around? What isn't floating around is these coordinate transforms, and the weights on the bets, to begin with at least. So we're going to get a score for how good a cluster this is. So let's suppose for this cluster, these red dots have very high posterior probability under the Gaussian, These ones are sort of can't decide whether under the Gaussian or the uniform, and these ones are under the uniform. And so we compute the sum of for all these data points, each weighted by the fraction of an observation it is, of the log probability of seeing that under a mixture of a Gaussian and a uniform. We also compute the log probability of seeing that just given a uniform. And our score is the difference in these log probs. It's important to use something like that because what you want is that if I put in a stray vote here, it doesn't affect the score. And it won't affect the score much. I mean, depending on how you do it, it won't affect it at all. Because that'll be coded under the uniform in both cases. But if you find a cluster, this score will be big. And if it's a tight cluster, this score will be much better. So now let's look at what it does. So that's the score. You then take this score and you put it into a softmax to try and make a decision about what class it is. And so you treat this as the logit that goes into softmax. You scale it first because that's a sort of hack. So there's a hack scale here. If everything was probabilistically correct, you should need a scale of 1, but you don't. And you look at the decision you make. If it's the wrong decision, you say up the score for the right guy, down the score for the wrong guy, and you backpropagate derivatives of that score through the whole system. So there's an inner loop that involves doing EM, and it only takes about 4 iterations. So you found the cluster. Now, I don't believe that's how the brain does it. That's just how this model does it. I believe the brain has to have some other way of solving this computation. But for now, that's the best I've got. I do that computation, and now I just learn the whole system. And after I've learned it, if you showed a digit like this, and you look at the scores that you get and the clusters that you get for the various high-level capsules, I'm not showing you all of them. There's other ones over here. I'm just showing you the first 2 coordinates, because I know those are going to be to do with position. And so the 0, it gets lots of very weak bets. Those are coming from patches that don't have anything in them. The size of a circle here is the posterior for that thing being accounted for by the Gaussian. This is at 2 standard deviations, I think. Yeah. And so the votes that you get for a 0 look like that. The votes that you get for a 5 look like this. They're much more tightly clustered. And so your Gaussian is a sharper Gaussian, which means it can give higher probability to things. So this is the log of the variance. And when the log of the variance is negative, that means it's sharp. This is a sharp Gaussian. That's a much less sharp Gaussian. This is the score you get. This is the difference between the probability under the mixture and the probability under the uniform. And this gets a high score, and the other guys get low scores, so it says it's a 5. One more example. So I'm showing you more of the digits here. This one, it gets a high score because it's a 6, and it's a tight cluster. This cluster's relatively tight. So this has a log variance of -1. This has a log variance of -0.5. So this is fairly tight. It's a bit 0-like. But it knows it's a 6. Now, a system like this does about as well as a convolutional neural network on MNIST. The difference is that if you take a Mach Air and you train a convolutional neural network, you can train it in sort of 10 minutes to half an hour. And if you take my Mach Air and you train this, it takes 2 days. And that's because this inner loop of doing all this EM to get the scores and stuff is very slow compared with just matrix operations through the neural net. But if we could find a fast way of doing that stuff, then this would be fine. But it actually works. It manages to recognize digits by finding the agreement in the pose predictions. That's one demo. There's another demo that's a bit more convincing. So there's all sorts of things that need to be done to make this better. We need multiple simultaneous digits. I can get that working. That's fine. In this example I showed you, we didn't redistribute the votes. We just did bottom-up votes. And we didn't reweight them based on routing by agreement. So I need to add, currently someone is adding routing by agreement to this, and it will work better. We didn't have deeper hierarchies. We didn't have real images. They're just MNIST. There's lots to be done. One thing we have done is tried to get the primary capsules not by back propagating the errors you make in digit classification, but by doing unsupervised learning. You'd like to do unsupervised learning to get from pixels to entities that have poses. So that first stage, if you can do it with unsupervised learning, it's going to be much less. You're going to need much less labeled data, for example. So, we want to de-render the image and get it to entities that have poses, unsupervised. And we have several ways of doing that. And here's what we'd really like to do. And to simplify the PowerPoint, I've just assumed we're getting two-dimensional pose, which is just position. But really, we were going to do this for full pose, which is a full affine. So you have an image, and you would like to go through some nonlinear units and get out in these different capsules. You'd like to get the position of an entity, and in this case, the intensity of the entity. So I've changed from a probability to an intensity, which is a slight fudge, which I need for what I do later. The work I'm describing now is work that was done in Taman Tielemann's thesis, which recently came out. So that's what we'd like to achieve. We'd like these to learn to be entities, and they decide what kind of entity they should be. And we'd like them to give us their poses and how much they're present. And the way we're going to do it is by having a simple graphics model. Oh dear, you see, I told you if you let the innatists in, then they'll take over. So we're going to have an innate graphics model now, but that's just for this system. And we're going to try and learn to reconstruct the image by first extracting the capsules and then reconstructing the image from the capsules, but using built-in graphics. So it works like this. You saw this bit already. This is going to learn, all these learn and all these learn. It's going to learn to extract some kind of entity and the pose of the entity and the intensity of the entity. And it knows which entity it is because it's these neurons. And then these instantiation parameters are going to be fed to the graphics system. And the graphics system from these parameters is going to have to reconstruct the image. And the graphics system is going to learn a little template for each entity. But what the graphics system is going to be able to do, unlike a normal neural net, is it's going to be able to translate this template according to this x and y. And it's going to be able to scale the template, scale the intensities here according to the I. And then it's just going to add it to the image. So you've wired in some graphics, and you're learning to invert graphics here. But it's going to also learn what these entities should be. What you've wired in when you wired in the graphics is just the ability to take some entity that you've learned and translate it. And more generally, do a full affine. OK, so now, if you ask what templates does it learn in modeling digits, these are the templates it learns. And you can see they're little pieces of stroke with feathered ends, so you can add them together and then make a nice digit. This is now the case when it can, yes, this thing can apply full affines to these templates. And so let's see how it now decomposes digits. So if you show it this digit, this is its reconstruction. And for each of its 10 capsules, this is the contribution from the capsule. So if you look at this capsule, it's making different contributions. But you'll see it's sort of found the corresponding pieces. For this 6, that part of the loop is coded here. For this 2, it's coding this piece of the curve here. For this 8, it's coding this bottom piece of the curve here. And so these contributions, when you add them up, do a jolly good job of reconstructing the digits. It works very well for reconstruction. OK, so far what we've done is we've learned bottom up to what the pieces should be, and we've learned how to look at an image and extract the poses of those pieces. So now, having done that unsupervised, let's now try and do some supervised learning on top of this. And remember, after you've got to poses, everything's linear, so life's going to be easy. So here's the idea, if we just had 2 pose parameters. You take each of the capsules and you take its pose parameters you extracted from the image, and you just concatenate them all. You get a big vector. And of course, if it's a particular shape, there's lots of mutual information between all these guys. They're all related in the right way. They can all change as you change your view on the shape, but they have relationships between them. So if you do factor analysis on this, factor analysis will find underlying factors, so 6 for the affine and 4 for the deformation, underlying factors that model this very nicely. Because as you change your viewpoint, all of this stuff is changing, and by changing the affine represented by the factors, you can model that perfectly. So the factor loadings, these 3 factor loadings here, will actually be modeling the relationship between the whole and the part. And by fitting a factor analyzer, if I just had 1 digit, I could do that. Now I've actually got a mixture of digits, so I'm going to fit a mixture of factor analyzers. It would be nice if I could just fit 10 of them, but that doesn't work so well. So we fitted a mixture of 25 factor analyzers. Actually, if you just fit a mixture of 10 factor analyzers, you can fit factor analyzers, a mixture of factor analyzers, you can fit it to the raw pixels. If you fit to the raw pixels, these are the means of the factor analyzers. If you fit the factor analyzers to the capsules, and then take what they tell the capsules to do and reconstruct from what they tell the capsules to do, these are the means of the factor analyzers. This is all unsupervised. So you can tell it's done a pretty good job. 4s and 9s is a bit confused about, but it's really nailed the 10-way, there's 10 classes here. And in fact, if you look at this factor analyzer, and you look at the 10 factors, and you look at what changing a factor does, if you take the mean value and subtract 2 standard deviations, you'll get that. And if you add 2 standard deviations, you'll get that. So this is a factor that's dealing with italicness. This is a factor for loopiness, and so on. Now in this data, we didn't actually do much affine transformation, so most of the factors are about deformation. If you use 25 factors, oh, forget that one. If you want to recognize digits with very few labeled examples now, what you can do is, you can do standard backprop. Standard backprop on MNIST with 60,000 examples gets about 1.6% error. And with all sorts of tricks, you can get that down to about 1%. If you do a very clever thing called scattering transforms developed by Bruno and Mallet, they were very pleased because they managed to divide that by a factor of about 30. Actually, with 30,000, you get 1.7, so say 15. With 2,000 labeled examples, they can do just as well. So they're getting much more statistical efficiency. They can get this error rate with 2,000 examples. If you do unsupervised learning of the kind I just showed you, and you have 25 clusters, that is, you do a mixture of 25 factor analyzers on these concatenated instantiation parameters of the primary capsules, after you've done that, you just take each factor analyzer and you say, for the example that I'm most confident should go to that factor analyzer, just tell me what its name is. Tell me what its class is. And so you have to ask 25 questions. And if you ask 25 questions, you can get 1.75% errors on average. So now that's much closer to what humans can do. You show them a lot of digits, and they ask you a few questions, and then they know how to classify these digits. And so this is an example where, because we grabbed the linear manifold, we made the unsupervised learning work right, so it found the natural classes. And having done that, you can learn with very few labels. Yeah, I just said all that. And that's the end. OK, I'm done. Unsupervised then? OK, so the question was, how does that compare with, there's people out there, how does that compare with doing unsupervised followed by supervised, like unsupervised pre-training presumably followed by supervised, is much, much better. So if you do standard unsupervised followed by supervised, if you say stack up autoencoders, you'll do about the same as the Bruner and Mallet. You won't do much better than that. Maybe you can get down to 1,000. But this is like almost 2 orders of magnitude better than that. Because you grab the linear manifold. Yeah.
Maybe another version of that question is, how would it compare with doing some kind of more generic mixture model, like mixture factor analyzers on pixels? Where, like I remember back in the day.
Yeah. So I showed you.
Model of MNIST, well, with like maybe about 10 mixture components per digit. So then you could let you learn about 100.
It wasn't nearly as good as this. So you can look at the purity of the mixture components.
No, it's clearly much better, but I'm just saying you could compare it to that.
Yes. I imagine, well, that just won't get you down to 1.7% errors.
But if you were able to sort of label, like if you were able to fit a pretty good 100-component mixture model.
Right. I think to get to 1.7% errors, you probably need to fix something like 1,000 components. I mean, I have to check up. I doubt you'd be able to do it with 100 components in there. I've tried those models.
Yeah, right.
I've tried lots of components, and with 100 components, I'd be very surprised if you could get down to 1.7%. Are you trying to get at the idea that actually their low resolution is helpful by suppressing details and they just see the sort of essence of it at low resolution and they can learn more easily?
Yeah, well, it's not just low resolution, it's a dynamic facet. Okay. But yeah, that's
possibly. I don't want to comment on it. I haven't thought about that issue, and I'd want to think about it before I said anything. I'm not disagreeing. It might be helpful, but I don't know. Hang on, when you say, why are humans so bad? The question was, a critical aspect of this is that the relational thing is hardwired, the fact that it's a linear transformation. So why are humans so bad at doing this rotational transformation of objects? So there's 2 things you might mean by why are they so bad. Humans are actually pretty good at recognizing objects in funny orientations. You're not good at doing very fine discriminations for that, but if I show you an upside-down face, you know right away it's an upside-down face. You don't know whose it is, but you know right away it's an upside-down face. So you do that kind of instantly. There's probably a 10 millisecond penalty for that. But the mental rotation is going to be like over 100 milliseconds to get it upright, so it's a different order of magnitude. So the things where you really have to do the slow mental rotation are to make handedness judgments, or to do things like, will this grand piano fit through this studio door, where you have to do physical. But recognition, you're actually pretty good at dealing with different orientations. That capital letter R I showed you, you instantly knew it was a capital letter R. And when I say instantly, within about 250 milliseconds. And then it took you 100 milliseconds to rotate. And if it was a 3D thing, you'd rotate it even slower. That was 2-dimensional. In 3D, you do mental rotation too, but it's quite a lot slower. For the learning?
Yes, for the learning. What kind of heuristics or computational approximations could you make to bring that time down, if at all?
I'm sure you can bring it down by a whole lot. You could start off by not programming it in MATLAB. Or even better, you could start off by not having me program it. That would give you about an order of magnitude. But the real essence of it is this thing that, what's different from normal neural nets here is that the core of it is something that looks for agreement between activity vectors. It's not looking for agreement between a weight vector and an activity vector. That's what a filter does. What we want is agreement between activity vectors, which is going after covariance structure. And that computation, to find these high-dimensional agreements among a whole bunch of random stuff, there must be ways to make that efficient. And I have some ideas about how to make it efficient, and I'll talk about those if they work. But that's what's slowing it up.
The capsules here are very visual. We're using neural nets for many other kinds of problems. Do you have ideas about what the features of capsules might be for other problems?
Some. So let's take speech. I have a long-suffering graduate student who I got to do a thesis. I'm trying to apply these ideas to speech. He was a very good student, and these ideas are quite difficult to get working on speech. But for example, you can say there's changes in frequency and changes in onset time and changes in amplitude. And you can try and get entities that tell you this complicated acoustic event is happening, and here's when it's happening, and here's what frequency it's happening at, and here's the amplitude it's happening at. And he managed, in the end, to get things that worked as well as standard neural networks using capsules ideas in speech. But they're more natural for vision. I'll leave it at that.
Any other questions? So let me remind you, there's a panel in this room at 6 on the path to intelligence, and in between, all invited to reception outside. Thank you.